Hi again. This is another in our series of what appear to be very popular videos on how to solve problems. This one deals specifically with solving op-amps. It's the first of a series. We're going to do a couple of these. And this picks a relatively simple circuit, but shows you how to solve it three different ways. That's what's key here. We solve it three different ways. And there are more ways I'm not even going to tell you or show you how to solve. I'll explain them as we're going through it. So there are many ways to solve these circuits. Of course, they should all lead to the same answer, but it gives you the opportunity to practice, which is incredibly important. That is the trick here. So you remember from the video where we describe op-amps, there are a set of steps that we go through. And we're going to use those steps here. The first step will be to replace the initial circuit with a schematic version of the op-amp, and then to label it with all the appropriate currents, voltages, with the plus and minus signs, all the things you need in preparation for Kirchhoff's tools. And please do the diagram carefully before you start drawing Kirchhoff's tools. Once the diagram is complete, then you have a look at it and say, now I need to decide on my Kirchhoff's tools. You'll need one that includes the input. You'll need one that contains the output. And other than that, it really doesn't matter. You'll have to also judge sometimes, depending on the complexity of the circuit, how many Kirchhoff's tools you need. Most of the ones that we have in this class, you'll be able to solve with two Kirchhoff's tools, because the current structure in the external circuit is either simple or can be simplified to the point where that's all you should need. And the second case I'll show you, second video I'll show you a slightly more difficult case. So once we have the Kirchhoff's tools picked, then we write them down. So we write an equation for each tour. I like to write them side by side, as you'll see. We then solve one of them, whichever one you like, for a current that is also apparently common in the second Kirchhoff's tool equation. Solve the first equation in terms of that current, substitute that current into the second equation, and then solve the resulting set of equations. Or actually, by this time, it'll just be a single equation. The key goal of all these problems will be to figure out what the amplification is. Now, that's a ratio, if you will, between the output and the input. The input may be simple, a single input, may be complicated, may have a couple of inputs. Again, there are different variations, but always the goal is to have an expression that says V out equals something times V in, or V out over V in is equal to some expression. And in that expression should only be values for the components you know, which would be the resistors typically. It won't be the amplification factor of the amplifier. We know that goes away because we treat that as infinite. So that's not part of the story. You should never see a current embedded in that expression. So there can't be a current. You have to substitute in such a way that all the currents disappear so that you only have values of resistors. Then you know you have a viable solution. Solve these problems in terms of variables, as I've said. Do sanity checks, do unit checks, make sure everything makes sense the way you want it. And then if you do have numbers at the end, finally substitute those numbers to figure out the actual ratios, amplification factors that particular circuit will enable you to achieve. And then, as another step, look at the output, even before you put the numbers in, look at the output of your equation, the output of your circuit, and say, what does this circuit do functionally? What kind of amplifier is it? Does it invert? Does it take a difference between two sources if there are two sources? Does it take a sum of two sources, or does it have just one source? So there are all kinds of different functions that we implement through op-amps, arguably even logical mathematical functions like a multiply function or an add or subtract function. Those are all things we can implement in op-amps. And so you should look at the output, and oftentimes we'll ask you this question, what function do you see in that representation? Okay, enough preamble. Let's jump to the computer or the iPad, and I'll walk you through one of these questions. See you soon. All right, so here's the problem that we're going to solve. It's another relatively simple op-amp circuit, but they make good examples to work through. And we'll start by redrawing that diagram and simplifying it to convert it from this sort of schematic diagram to something that really just describes the op-amp. Okay, so there's my diagram, and now I'll clean it up and turn it into the schematic form that we really want to deal with. And the first thing is that you remember we can kind of get rid of the whole op amp itself. We can remove that from our diagram or draw a diagram without it. And now we're left with what we need. But of course now we have to start doing things like picking the currents and signs and all that good stuff. So we'll pick this current up here. We'll call it IS, which again we know already is the same as the current through the feedback resistor. And as soon as we draw that current, we have no choice but to draw positive there and negative there and positive here and negative there. And then we can name these voltages here the negative input or the positive input. We can, we're not going to use that for anything, but it doesn't hurt to add it. We have our source voltage still down there as before, and our various resistors. So now we have really the starting point we need, and starting point that we need, and now we can go ahead and perform the circuit analysis. And of course we do that the way we've been doing it all along. That's through Kirchhoff's tours. And I'm going to show you 3 different versions for how to solve this problem. So maybe we'll say version 1 right here. So to keep in mind, and I'll put this file out on the Canvas page as well. So what I'm planning to do here is write down the 2 Kirchhoff's tours, or first pick 2 Kirchhoff's tours, and then write down the equations that go with them, just like we normally do. And you remember from the instructions that I have to pick one Kirchhoff's tour that includes the input. So I'll draw one that looks like that. We'll call it KT1. And then I need one that contains the output. And so what I'll do is I'll take one that goes around this whole way out here and then down across from there, and I'll call that KT2. So those are my 2 Kirchhoff's tours. One contains the input, the Vs, one contains the output, the V0, and that's a great place to start. So now I can start writing down some equations. So I can say from KT1, and I like to lay them out this way, where I put IS times RS plus Vs, and you can see we've just gone around the loop respecting the sign conventions, equal to 0, from which I can easily write IS is equal to minus Vs over Rs. So now I've isolated that KT1 and also simplified the current expression. Now I can say from KT2, and oftentimes I'll write them this way. I'll stick a little label KT1, KT2, so I know what I'm deriving this information from. So now I can look at KT2, which is this much bigger loop. Again, we go through Vs, in this case from a negative direction, so we're at minus Vs, and then we go through the VPVN, but we said there's no voltage drop across there. We have no voltage difference because the infinite input resistance, so we can just skip over that essentially and go up to the feedback resistor and write down the term there, and that's going to be positive because we're heading into the positive end of that resistor, times RF, and then we come around to the output voltage, and we've seen the signs there, so that's V0. Sum of that is equal to 0. So now, again, I can solve it different ways. Maybe the simplest thing is I recognize that I have an IS on the right and an IS I figured out on the left, so I can just substitute in there and write down the expression for minus Vs plus, and now I'm going to have a minus actually from that first term, so I'm going to change that into a minus Vs over Rs times Rf plus V0 equals 0. So now I have something pretty close to useful. I have everything in terms of voltages and resistors, and now I have to say, well, what am I trying to do here? I'm trying to solve for V0 as a function of Vs. So now I can write V0, put it on the left hand side because that's where I want it to live, and then I can move all the other stuff over to the other side, and that becomes positive Vs. And now I look and I have Vs there twice, so I can take the Vs out of the first term and replace that with a 1, and now again I have a plus because I've changed signs, and what I see here is I have an Rf over Rs, and that's my solution. Done. So now I have to look at that solution and say, what do I have here? I have an amplifier, hopefully that's what we're building. I have an amplifier that multiplies the source voltage Vs by a factor 1 plus Rf over Rs. And I can of course dimension Rf and Rs to give me whatever amplification I wish and multiply it by Vs. So I have a non-inverting amplifier circuit versus the inverting one that we did in the notes for the lecture. So now I told you that I could do this different ways. So let me take this diagram again, and now I'll say, okay, I want to change things. I want to take some different tours because I promised I could solve this different ways. So for this particular approach, I think I'll leave K2 the way it is, and I'll just change K1. So let me get rid of that line here. So I'm getting rid of the K1 tour carefully. Trying not to mess things up here. Okay, so I have my KT1. Now where's KT1 going to go? Okay, so it's going to go around and pick up, because I have in KT2 I have the output and the input. I've met the requirements actually for that I need to do, so I can pick a pretty different tour now and be fine with it. So I'm going to pick one that goes up along here and over there and loops around the whole circuit and also includes the output and comes back across the bottom. And that is going to be my new KT1. So this will be version 2 of solving this problem. And just as before, I'm going to say KT1, and now I have a different KT1, so I have to figure that one out. And I'm going to follow the same current, the same IS. So I'm going to have IS times RS plus IS times RF plus, now we go all over to the right here, plus V0, and that's going to be equal to 0. And just as usual, I take IS and I say that's equal to now minus V0 over RS plus RF. Straightforward, right? So now KT2, and that should look familiar because it'll be the same as we had before, where we said minus Vs, and then we have the loop all the way up to the feedback resistor IS RF plus, plus, got to remember the V0 term, so I have the V0, the output term here, and those are all equal to 0. And now I can do the same substitution trick as I did before. I can take this value for IS and plug it right in here, and that will give me and now I can start to sort of anticipate a little bit what's going to happen. So I can say I have a V0 over here that I already have. Now I'm going to have plus, and now IS is going to have V0 in it too, only it's negative. So I'm going to have to change the sign there and say minus IS, which is minus V0, and then I'm going to have my RF term from there, and over RS plus RF. And then on the other side, I'm going to have my, again, I'm going to switch the terms around, and sorry, the Vs is going to go on the other side, and it'll be plus, so it'll change signs, and I'll get a Vs over here. Okay, so now we can simplify this expression on the left by noting that we can rewrite it as V0 times 1 minus RF over RS plus RF. And that is equal in turn, because I can put this over a common denominator, to V0 times RS plus R, sorry, that should be an F there, RS plus RF minus RF all over RS plus RF. And that in turn is still equal to Vs. Now of course the RFs cancel, and I'm left with V0 times, and again RS is left what's left over here, plus RS over RS plus RF. That's equal to Vs, and that in turn is, I can simplify further. Let's move down to another page here. That I can simplify further by saying that V0 is equal to, by cross multiplying, RS plus RF over RS times VS, which still doesn't look quite like what we're used to seeing before, but then I recognize I can rewrite this even more and say that's actually 1 plus RF over RS times VS. And that's the form that we saw before, exactly the same form that we had. And so that's now our solution that we have for this problem. We can even draw a little box around it here. So that summarizes the solution by version 2. Okay. Now we can start again by pasting in the figure again that we had before, and we can solve it using version 3. Oops. Don't learn how to write here again. Version 3. So now what am I going to do differently from the other two versions? Well, what I'm going to do now is take a Kirchhoff's tour, the same as the Kirchhoff tour I have there for version 1, but now I'm going to change the one I do for Kirchhoff's tour 2. So let's erase that carefully. And this one will actually finish the same because it has to include the output, but instead of starting with the input, because we have the input already covered in KT1, I can draw another one that starts up here and goes around this loop. Connect those up, and that's KT2. So now I can do the same thing as before. KT1, write down the expression for that, and that's our IS times RS plus VS equals 0, from which we write the somewhat hopefully familiar by now term of minus Vs over Rs, and over here on KT2 I have another expression, so I have the same IS current, but it's going to flow now, and I'm getting smarter at this now. I recognize it's going to flow through RS and RF, so I can actually combine them already, anticipating what's going to happen. And then of course I have the output voltage V0, and the sum is equal to 0. And again, the same trick as before. I substitute in here for the IS current, and now I write a minus Vs over Rs times Rs plus Rf equals, well, we can do this way, minus V, put my V0 on the other side, and of course those signs will cancel, and I can already write down V0, isolating that, sort of swapping sides, is equal to, and now I have this term Rs plus Rf over Rs times Vs, and again we can simplify this quite easily and say that that's equal to 1 plus our now familiar Rf over Rs times Vs. And now we have the same solution that we've had all along. And that's the solution for the problem in the third version 3. So just to remind you again, the strategies that we've used here are first of all to look at the original figure, see how many unknowns we have, how many internal variables we have to keep track of, mark them on the circuit, the simplified version of the circuit, and then pick a couple of Kirchhoff's tours. And we've seen here there are 3 different choices, even in a simple problem like this. So pick one that contains the input, at least one that contains the input, or one that contains the input and maybe the output. So anyway, the input and output have to be both covered, and then we can quite flexibly go forward and just do what we've been doing, and that's apply the KT1, the KT2, solve for current, substitute it. I could have also used in this problem, I could have solved this expression over on the right here. I could have solved that in terms of IS and set the two IS's equal. It's just another form of solving those two simultaneous equations. That I leave up to you to figure out what your favorite strategy is for that. And in the end, we can simplify, and it's always important to keep in mind, what am I trying to do? I'm trying usually to figure out an amplification, which means I need an output voltage on the left and an input voltage on the right, and then the factors that are left over should be all resistors, or really resistors. There's no other parameters that you'll see in these circuits. And if I have a current that's still around, if IS were still lingering in one of those equations at that latter point, if I got down to this point here or even this point here and noticed I had a current, then I'd know that I'd made a mistake. And that's just a warning to go back, rethink, regroup, and try it again. So that's really all there is to solving these equations. But this should be enough for you to do the homeworks this week. And we'll look forward to next week and getting into a little more challenging problems. Thanks a lot. Bye-bye for now.